So welcome back. As per my promise, we are going to talk about atmospheric pressure and gauge pressure and about the barometers and the manometers in the first instance. And as we discussed before, the atmospheric pressure turns out to be at the surface of the sea surface all over the world. Mostly this has been measured and it was found that it is 1.013 into 10 to the power of 5 pascals, which is Newton per meter square. Okay, and it's called a pressure of 1 atmosphere. So this is under the condition of what we call as TP or TP, etc. And this was measured for the first time by another French scientist, Torricelli, who lived a very short life again of 39 years, just like Pascal, and he measured it for the first time, the atmospheric pressure, and it was expressed, the atmospheric pressure was expressed to be equivalent to a 76 centimeter or 760 millimeter of mercury column, and it can be calculated by using the formula which we have already discussed. PA, atmospheric pressure, is equal to rho GH. So the value of G to be around 10, okay, and rho for mercury 13.6 into 10 to the power of 3 kilogram per meter cube. We calculate the value of H. If we put this value in the calculation, reverse calculation can make it equivalent to 76 centimeter or 760 millimeters of mercury column. If we instead take a column of water, then this will be 76 centimeters multiplied by 13.6, which is about 10 meters. Okay. But among the available liquids, mercury is a liquid which has got the highest density. Okay, and so we can have this pressure expressed in rho GH, and the pressure equivalent of 1 millimeter we can calculate this to be equal to 1.013 into 10 to the power of 5, which I can write as 101300 divided by 760, and it turns out to be 133 pascals. 133 pascals is defined as, honor to Torricelli, is defined as 1 ton, and this pressure or pressure difference, this is what is used in the faculties of medicine and physiology, or in measurement of things in that department, as 1 torr, like that. Okay, the pressure difference. The common unit of pressure in meteorology, in the weather systems, that is taken as 1 bar. Bar is also a word which indicates pressure, and 1 bar is equal to 10 to the power of 5 pascals. In fact, PA is approximately equal to 1.013, and if we take the approximation, it turns out to be 10 to the power of 5 pascals. So one of the favorite units is a millibar. Milli means 10 to the power of -3, and is equal to 100 pascals. Taking into account, let us talk about the mercury barometer. Was for the first time used by Torricelli. This is a trough filled with mercury, and then there is a long tube which is first of all filled with mercury, and then this is put in the mercury column in this trough, and you see that there is air over here, and from here to here, from this level to this level, the height is h, and it balances the air over here, and of course the pressure here is the atmospheric pressure, and this pressure is measured in terms of the h into rho into g of mercury, and that is measured to be 76 centimeters of mercury. Okay, small column by all means, and of course this is the level at the sea level, but sometimes what happens is that the atmospheric pressure sometimes it becomes low. When the pressure drops down by 5% to 7% like that, then there is an indication that winds are going to flow from levels of higher pressure to levels of lower pressure. Okay, so the next item after the mercury barometer, we are going to talk about the open tube manometer for measuring the changes in the value of pressure. So in the open tube manometer for measuring delta P, we have an arrangement like this. This is a glass bulb, transparent, and we put the liquid in it, okay, and naturally this is the pressure which we have to measure here, and we have the atmospheric pressure, okay, which is because the column is up to this height, and if A and A dash at the same height and there is an arrangement for measuring the height of the column, whether the column is mercury or some kind of a immiscible oil. So we use mercury for measuring large pressure differences. These are the gauge pressures actually, and oil for small changes in the value of pressure. So we can measure with the help of this open tube manometer. Okay, first of all we were having a barometer, now it is manometer. Okay, so in the measurement that we carry, we use a very simple relation, that the pressure minus the atmospheric pressure is known as the gauge pressure. We write it as P minus PA is equal to PG. Okay, and because everywhere on the two sides of this U tube that we have, the pressure is the same at the same level, same level. The pressure is the same at the same level on both sides of the U tube. Okay, so we are not concerned with that. As to what is the pressure, the two sides, we are concerned about the pressure difference, the delta P, that we can obtain by measuring the height h, okay, which may change according to the value of the pressure here. That height can change because the two are interrelated. If the value of P becomes much more than value of PA, then the column height has to be more and more. Okay. Now, one of the properties of the liquids that we take is that the density of the liquid is almost constant over a wide range of temperature and pressure, because I told you that the liquids, like solids, are kind of incompressible. they are incompressible. But in certain circumstances, suppose we take air or some kind of gases as what is we have to use here in the manometer. If gases are taken, the gas is not incompressible, okay, then there is variation and you have to be careful about it. For the liquids, of course, by the way, for example, we can use, we can measure the pressure at the sea level, okay, and then if we know the density of air, which is normally we take at the STP as equal to 1.29 kilogram per meter cube, we can estimate, I'll not call it a calculation, we can make an estimation that if the air column has got the same density and the same value of G is there at all heights, where we'll calculate this air, the estimation is that the air height above the surface of the sea is about 8 kilometers, which is not true, because as we go up, the gases are rarefied, and because they will follow what is known as, and we'll come to that, the Boyle's law, PV is equal to nRT, okay. The pressure becomes smaller and smaller because the volume will change for the same amount, same mass of gas, and also the value of G, which will turn out to be is given as, and we found that the value of G at height h, remember, this is value of G at the zero level, 1 minus how much? 2h upon r. So the value of G also keeps up on changing if we have the column, the air rising high and high. That I'll show with the means of a few calculations in the shape of a couple of examples. So using the Pascal's law and the measurements that we have done, let us take up a numerical problem, just an estimation problem, where we have given the density of air is equal to 1.29 kilogram per meter cube, and of course we take that it is not a function of altitude, does not change with altitude, as also the value of G is also not a function of h. So under these two things, under the consideration that we take the value of rho as 1.29 kilogram per meter cube, we can calculate the height of the atmospheric column, the air that's above the surface of the sea, and then it is a very simple formula that we are going to use. Our musical friend rho gh is equal to, I'll substitute the value of rho as 1.29. I'm setting aside that kilogram per meter cube from here. 9.8 is the value of small g at the surface of the earth, which we have taken not to change with the value of height, and 9.8 kilogram per meter per second square, and h in meters or whatever, and this is equal to 1.01 into 10 to the power of 5 pascals. So if we substitute the values and estimate the value of h, I get it as 1.01 10 to the power 5 divided by 1.29 into 9.8, and this turns out to be equal to 7989 meters, which we can roughly say to be 8 kilometers. But that's false. That's not true. Here we have taken two constraints. One about the density of the air, that it remains the same throughout that column, and the other, the value of G also remains the same, is equal to the value of G at the sea level. Okay. So what we can see that the rho actually is a function of height. Okay. So, and G is also a function of height. So when we estimate, when we make amends for these things, then the actual height of atmosphere is about 100 kilometers above the surface of the earth. Of course, we can use the formula GH is equal to G 1 minus 2h upon R, where R is the radius of the earth. And then practically what we find is that as the altitude is increased, as the height is increased, so the pressure keeps on decreasing and decreasing. However, this graph which we have drawn over here is a deviation from the graph y is proportional to 1 upon x. Okay, because there are many other things about the variations of the value of h and the value of g at different heights. We have to keep on the estimates of small columns and go ahead and build up. Okay, so this is what we say in English, that there is many a slip between the cup and the lip. Okay, so things are a bit complex and complicated. However, this value that estimate I have just told you is a true value. Now, before I move on to another exercise, well, the value of G at the surface of the moon, Gm, is approximately 1/6 of the value of G on the surface of the earth. Okay, so one can ask you a question, where one tries to be smart and tries to teach you what is the column of atmosphere at the surface of the moon. And the answer is, my dear friends, because no gas can survive on the surface of the moon, so therefore there is no atmosphere, and therefore we cannot, so that is equal to whatever you think. I'm just pointing it out to you. So there is another example of the deep seas, where there is a submarine at the depth of 1 kilometer, 1000 meters, and it is in the sea water. Of course, the sea water, the density is 1.03 into 10 raised to the power of 3 kilogram per meter cube, and of course we consider that the density is not a function of the depth. Okay, so everywhere we consider that the same density exists, which is not true. However, now what we have to calculate is the absolute pressure experienced by the submarine, the gauge pressure, and the force on a window of area of 400 centimeter square, which turns out to be equal to 0.04 meter square. These the values can change. Okay, so the only value that I have given to you is there are two values. One is the depth here, and the other is this area like this. They can be changed, and so our estimate will vary, our estimate will also change. Now, the value of G is taken as 10 meter per second square in this estimation, in this calculation, and we consider that G is not a function of the depth, which is not true. You know that here I have the formula that G at this depth h is equal to how much? G on the surface 1 minus h upon r. And remember the difference between this formula and the formula for the height of the surface of the earth, and that is how it happens. But here we give you the leverage that the value of G, the acceleration due to gravity or the field at a given depth is the same as that at the surface of it. So let's estimate the absolute pressure, which is given by the atmospheric pressure plus rho G H, our friend. 1.01 10 to the power of 5 plus this into this into this. Of course, the value of G has been taken as 10. And H. This is not 100. This got to be 1000. Okay. So 1000 meters. This turns out to be 104 atmosphere. If we make out the calculations, we find this is equal to, of course. So this is multiplied by 100. This is 103, and this taken as equal to 1. So 103 plus 1 is equal to 104 atmosphere. Now the gauge pressure, that is equal to 104 atmosphere minus 1 atmosphere is equal to 103 atmosphere. It's very easily calculated for the present set of data, and the data till now is only 1000 meters down the surface of the earth. Now let us say that the pressure outside the window of the submarine is 104 atmospheric pressure, and that inside is 1 atmospheric pressure. So the gauge pressure is how much? This minus this is equal to 103 atmosphere, which we have calculated over here. And then the force, that because pressure is force divided by area, so the force becomes equal to pressure multiplied by the area. I put the values over here, 103 10 to the power of 5, 0.04, and it turns out to be equal to 412,000 newtons, which I am writing here as 4.01 into 10 to the power of 5 newton. Two values are the one and the same, but I tell you that this is the value which is the preferred value. This is the scientific method of writing numbers. 4.01 into 10 to the power of 5. Okay, so you can go back and see why I have written like this. Next, I will be talking about the hydraulic machines, the hydraulic brakes, and buoyancy. I'll talk about Archimedes. Eureka, Eureka, Eureka. Okay? The naked scientist running on the streets of, in the nearness of Greece, because he had discovered something, so he was very happy, and he didn't know that he couldn't wait, and he said, Eureka, Eureka, Eureka. Those things, they follow suit. I again ask you to question. You question and we answer. That's our motto. So please do comment in the comment section, and I'll appreciate that, and I will delve into answering your questions to the best of my knowledge and to the best of my ability. I can even consult some of my esteemed colleagues who can answer your questions better than me. Thank you very much. See you soon.